So this is lecture 20, and we are discussing eigenvalues and eigenvectors, eigenvectors of a matrix. We started on this topic last time, but let's just quickly recall what we did. So if you have a matrix A, and for it you write this equation, that it acts on a column vector, and this A is an n by n matrix, acts on a column which is n dimensional column, so it's going to return you the column, an n dimensional column. But if it returns you the same column multiplied by some number, then then x is called that this is a eigenvector of A, and this lambda is said to be the eigenvalue, an eigenvalue of A. This is an eigenvector of A because there can be more than one eigenvectors and there can be more than one eigenvalue of A. And this equation is called the eigenvalue equation. Now, typically what you have is you have many eigenvalues for a matrix. So this equation is not satisfied for any arbitrary numbers. It's satisfied for very specific values of lambda, a few of them. So how to find the values of lambda for which such an equation holds? Well, you write it in this fashion. You bring all of these to one side so that you have zero vector on the other. And this you can write as action of this matrix on this column to give you a zero. Now we know that these will have non-trivial solutions are possible only if A minus lambda I is not invertible. So it's very important. It's a negative statement. It's not invertible. Or in other words, if determinant of A minus lambda I is 0. So in other words, you want those lambdas for which this equation holds. So this gives you, this equation is called the characteristic equation and gives you a polynomial of degree n in lambda. So when you open it up, you have this lambda going into the determinant is appearing on the diagonals, and when you open up the determinant, you are multiplying it again and again, and at max you get the nth, well, you definitely get one of the nth power of lambda, so you generate a polynomial of degree n. So you solve for this polynomial, you're putting it equal to 0. So I can write it that you have for this matrix, you have a polynomial in lambda and you're putting it equal to 0. So you solve for these solutions. These are called the roots of the polynomial. The values of lambda for which this polynomial is 0. And if you have a polynomial of nth degree, we have n roots. That means you have n eigenvalues. So for any matrix which is n by n, you will have n eigenvalues for that matrix. But two things to keep in mind. Some of these roots, which are just the eigenvalues, may be repeated. So you can get the same eigenvalue a few times, and you count that multiplicity. So in counting that n, for example, if you are having a 3 by 3 matrix, two of them may be same, and one of them would be different from those two. So in those three roots, two are same. So you still count it as three roots. And some of them may be complex, because there's no, when you say that a polynomial has n roots, polynomial of degree n has n roots, that theorem is proved in complex number. It's only in complex number that you can find all n roots, generally speaking. So some of these eigenvalues may be complex, and if you are multiplying your vector over here with a complex number, then you should be ready to consider complex multiplication of vectors. So your vector spaces then become complexified. You allow multiplication of vectors by complex numbers. Everything goes through, is just that instead of using the real numbers, now you use complex numbers. Similarly, then you allow your matrices to be having entries which are complex. So the field in which you work, the number system in which you work, you allow it to be a bit larger to capture all the possible eigenvalues. And how to find this is how you find the eigenvalues, how to find eigenvectors. Well, you put, so suppose you have found an eigenvalue lambda 1. For each eigenvalue, you will have an eigenvector. You put this eigenvalue back in here and look at this equation. This is your eigenvalue equation, because this I have got from here. Just brought the things on the right hand side to the left, and I get this equation. Then I solve it. I plug in each eigenvalue, like over here, I'm supposing that lambda 1 is an eigenvalue. You plug back in, you get a matrix over here, which is acting on x and giving you 0. So you find non-trivial solutions for this equation for x. Which we have done before, is just equivalent to, this is just given a name, finding the null space. All those vectors which give you 0 over here, finding the null space for this matrix. So this would be like finding the eigenvectors. And let's do, we did an example last time. I'm just going to do many more examples today just to make everything very clear. So suppose this is a matrix given to you. And you have to find the eigenvalues and eigenvectors. Find eigenvalues and eigenvectors. So I construct this matrix, which is take this matrix and subtract from it lambda times I. So it's 2 minus lambda minus 3, 1, 1, minus 2 minus lambda, 1, 1, minus 3, 2 minus lambda. So effectively, just on the diagonal entries, you subtract minus lambda every time, because you are always subtracting minus lambda I. And then you compute the determinant of it and put it equal to 0. So the determinant is just the determinant of this matrix, which we just constructed. And put equal to 0. So when I open this up, I get 2 minus lambda, and then I'm just constructing the full determinant, minus 2 plus lambda into 2 minus lambda minus into minus 3 into 1, which gives me a plus 3. So this minus this. Then I have the next term, which is minus times the next element in the first row. So that becomes plus 3. And then this minus this. So that gives me 2 minus lambda minus 1. And then plus the third entry, which gives me these two. So minus 3 minus into 2 plus lambda. So this gives me plus 2 plus lambda. That's just writing out the determinant for this matrix. So what does it give me? It gives me 2 minus lambda. And if I open this up, I have I can take this minus inside. I will have lambda minus 2. So lambda minus 2 into lambda plus 2, that's going to give me lambda square minus 2 square, which is 4, plus 3. Then I can take a minus common. So I have a lambda minus 1 inside. Then I have lambda minus 1 from here. This is still writing out the determinant. So this is now our polynomial. This is the polynomial associated with lambda, and we are going to try to put it equal to 0 and find its root. So just to find its root, I'm giving it a better form. So over here, I got lambda square minus 1, and I have minus 3 lambda minus 1 and plus lambda minus 1, so it gives me minus 2 lambda minus 1. And this, I can break it up like this. And now I can take, because each one of them has a factor of lambda minus 1, so I can take that common. So lambda minus 1, I take it out. So I am left with 2 minus lambda, lambda plus 1, and minus 2, which then gives me lambda minus 1, and when I multiply these out, I get a minus lambda square, then a plus 2, then minus lambda, and a plus 2 lambda, which gives me a plus lambda, and I have a minus 2 coming in from here. So these two cancel, and I have lambda minus 1 minus lambda square plus lambda. So I can take a lambda common, minus lambda common. I have lambda minus 1, lambda minus 1. This is equal to, this has to be put equal to 0. Now, once you factorize, if you are lucky enough to factorize the polynomial into these factors, each one of them have only one first power of your variable, then it's very easy to read off the roots. So roots over here, roots are, you just put each one of them equal to 0, one by one. Lambda is equal to 0, lambda is equal to 1, and the last one also gives me lambda is equal to 1. So this is an example where you have a repeated root. You have three factors, three roots, but two of them just happen to be same. So that means the eigenvalues of the matrix A are these. Lambda is equal to 0 and lambda is equal to 1. It's just that you have to remember, you can write it over here, or you can just keep it in your mind that one of them is repeated, because you expected 3. You know that they're going to be 3, but it's just that one is repeated. Now we have found the eigenvalues. Now we want to find the eigenvectors. So eigenvectors, what are the eigenvectors? So now the eigenvectors, since they are they correspond to null spaces of some specific vector, I put in my specific eigenvalue inside the eigenvalue equation. So the matrix I get, so I put one eigenvalue over here, construct this matrix, and solve this. So I know this is like finding the null space. So for each eigenvalue, I will get a subspace of my full Rn. So eigenvectors for each eigenvalue form a subspace. So I know, how do I get rid of this thing? So we have to solve this equation, and now we can just use our methods. So this is just revision of what we have been doing in the course for a long time. It will just be a good revision of that and putting those ideas into some application over here. So I'm just trying to find the eigenvalues using this equation, eigenvectors using this equation, and I have to use all the lambdas one by one. So for lambda is equal to 0, the eigenvectors will be found using a minus 0 I x is equal to 0, but this is just a x is equal to 0. So I have to find the null space of A itself. This is A. And I have to find a non-trivial solution, which gives me zeros on the other side. And I know I will be able to find it because I had this lambda is equal to 0 as an eigenvalue. I knew that the determinant is 0. So they have to be non-trivial solutions. So how do you do it? Just your usual methods. Bring it into reduced echelon form. So minus if well, first thing I can do, I need a one pivot on the top. So I can, for example, exchange row 1 and 2. So I just exchange row 1 and 2, exchanging these two. Now I multiply the row 1 by minus 2. Multiply row 1 by minus 2 and add it to row 2. I get a 0 here. Mm, 4 minus 3, I get a 1 here. Minus 2 plus 1, I get a minus 1 here. Then I multiply row 1 by minus 1 and add it to the third row. Gives me a 0 here. 2 and minus 3 gives me a minus 1 here. Minus 1 plus 2 gives me a 1 here. Now I have to take this as pivot. I multiply row 2 by minus 1 and add it below. No, I don't have to multiply it with anything. I just add it below because they're just gonna cancel. So I get a 0 here, a 0 here, a 0 here. And I was expecting a 0 like that because I needed non-trivial solutions. So I was expecting a 0 to appear. Now from here, I can go to the echelon form, reduced echelon form by taking this pivot and making things above it 0 as well. So this remains like before. This remains as before. And now I multiply the row 2 by 2 and add above. So minus 2 plus 1 gives me, so I'm multiplying row 2 by a 2 and adding above. So minus 2 plus 1 gives me minus 1. This is my now final echelon form. if I write this vector which I'm trying to find as x1, x2, and x3, then this tells me that x3 is a free variable. And the second equation tells me x2 minus x3 is 0. And the first equation tells me x1 minus x3 is 0. So if I put x3 is equal to some arbitrary alpha because it's free, then x1 is also alpha and x2 is also alpha from these equations. So this tells me let me just change the color. This tells me that the eigenvectors are of this form. So there is a one-dimensional space. You don't get just one eigenvector, you get a whole lot of them, a full one-dimensional space, which is generated by, spanned by this. So this is a typical situation. For one distinct eigenvalue, when you find the eigenvector, you get a one-dimensional space. So you can pick one representative of it, one particular eigenvector, and then you know that the rest would be just multiple of this because it's a one-dimensional space. So you can just say that this is the eigenvector, but then you know that any multiple of this eigenvector will also be an eigenvector. So you got this one-dimensional space as your eigenspace for this particular eigenvalue. So this is the eigenspace of eigenvectors corresponding to particular eigenvalue. For each eigenvalue, you get a different space. 0. And what is this space? It's this space with alpha arbitrary. Now, what about the other eigenvalue? Now we have this one. This eigenvalue, it was repeated, but it's only one. So we can start with it and construct this matrix and find its null space. Or find the non-trivial solutions of this. So now I'm putting lambda is equal to 1 in this equation. So my matrix turns out to be 1 minus 3, 1, because my original matrix was, what was it? 2 minus 3, 1, but from 2 I'm subtracting minus a 1 because lambda is the eigenvalue. So I get a 1. Then on this entry on the diagonal, I had a minus 2. I subtract a 1, which is the eigenvalue. I get minus 3. and then 1, 1 minus 3. I had a 2 here. I subtract minus 1. I subtract a 1 from here. I get a 1. So this is my augmented matrix. Now I can just subtract the row 1 from row 2 and row 3. Multiply row 1 by a minus 1 and add it to row 2 and row 3. I get a 0, 0, 0, 0, 0, 0. So it goes into the reduced row echelon form in a single stroke. And this means that x2 is a free variable, x3 is also a free variable, and x1 is 3 times x2 minus x3. So that means x1 is 3 alpha minus beta. Therefore, the eigenvectors take the form x1 is 3 alpha minus beta, and x2 is free, x3 is also free, where alpha, beta are arbitrary. So this I know because it's a null space, so it has to be a subspace. It is, because I can break it up like this. It's an eigenspace, it's a subspace. I can pick up the two vectors which span it. I can find its basis because I can break it up like this. So this is the eigenspace. And since I had two repeated eigenvalues, so my expectation was that I will get a two-dimensional subspace, because there were two eigenvalues, and for each eigenvalue I should be getting some kind of a line. So I get a two-dimensional subspace where these are the span. So these two vectors are they form the basis for the eigenspace, and any vector picked up from this eigenspace would be an eigenvalue vector with eigenvalue 1. So for examples would be, I can take alpha is equal to 1, beta is equal to 0. So this is an eigenvector, but then this is also an eigenvector corresponding to beta is equal to 1, alpha is equal to 0, and any linear combination of them, a sum of them with alpha, beta 1. This is also an eigenvector with same eigenvalue 2. We can check, for example, this one. Let's check this. So our original matrix was 2 minus 3, 1, 1, minus 2, 1, 1, minus 3, 2, and I multiply it with this eigenvector and check, do I reproduce it back, and since eigenvalue is 1, it should be multiplied by only 1. It should come back as it is. So I get 2 times 2, 4. 4 minus 3. Well, let's write minus 3 plus 1. Then 2 minus 2 plus 1. Then 2 minus 3 plus 2. So it indeed becomes 2, 1, 1. So it does come back. So it is an eigenvector with an eigenvalue 1. We have just checked. And since it gets multiplied with just 1, so this is the eigenvalue. We could have checked, let's just for practice, this one which we had found, the previous eigenspace for lambda is equal to 0, that 1, 1, 1, that gets killed because it gets multiplied by 0. So I should be expecting if I multiply this with 1, 1, 1, it should get killed because eigenvalue is 0. So that makes everything inside 0. So you can check. On the left hand side, I get 2 minus 3 plus 1, 1 minus 2 plus 1, 1 minus 3 plus 2, which are all 0. Let's do another example. This time, let's take a 2 by 2 matrix. Again, to find the eigenvalues, you just have to do this thing. So subtract lambda from the diagonal entries. And put this determinant equal to 0. So I get 1 minus lambda square, and minus times 2 into minus 2 plus 4 is equal to 0, is minus 4. So now if I take the square root, I will get, well, let's write it. I will get minus, square root of minus 4 is 2 iota plus or minus. So since it's a second order polynomial, so I know I'm going to get 2 roots, which in this case are very easy to find. It's just that you take the square root and you collect both roots, that one's plus and one's minus. I have done this thing. And square root of 4 is 2, square root of minus 1 is iota with a plus and minus. So that means the 2 roots are 1 minus lambda is equal to 2 iota, which gives you lambda is equal to 1 minus 2 iota, and the other root is 1 minus lambda is equal to minus 2 iota, which gives you lambda is equal to 1 plus 2 iota. So these are the 2 eigenvalues. And we can find the eigenvectors as well. Now, to get the eigenvectors, I have to consider this. Let's do it first for this value, 1 minus 2 iota. So what does it give me? My matrix was 1, entries were 1, 2, minus 2, 1. So on the diagonal, when I subtract this eigenvalue, 1 minus 1 gives me 0, and minus times minus 2 iota gives me 2 iota. Then 2, then there was minus 2 here, and again 2 iota. Because on the diagonal I had a 1. Zero, zero. Now I can multiply by a half throughout. That's an allowed operation. Multiplying each row with any number you like. Now, if I multiply, now it's just that now I'm dealing with complex number, nothing more complicated. Everything else remains same. I want to bring it to echelon form, so I want to bring 1 over here at the first spot. So how do I do that? I can multiply by minus iota the first row. What would I get? Iota into iota is minus 1, and then I have an extra minus 1. So that gives me 1. And over here I get a minus iota. Now I simply add the first and second row. The first row to the second row. I get this. So I've got my reduced echelon form, which is telling me that if my eigenvector is like this, then x2 is free, and x1 minus iota x2 is equal to 0. That means x1 is iota times x2. That means x1 is iota alpha. So therefore, this eigenvector is of this form. Iota 1. And if you want, so this is now, since I'm allowing the complex values, so I'm allowing alpha to be from complex numbers. Alpha is a complex number. And if I want, I can multiply it by, this is the basis vector, by an iota, then it would be just minus 1 iota. Still an arbitrary complex number. Any one of this works. Because you can multiply this vector by any number. So I just multiplied it by an iota to give it this form. What if I consider the other eigenvalue? For eigenvalue, what was the other one? 1 plus 2 iota. So now when I do 1 minus 1 plus 2 iota, I'll have a minus 2 iota here, a 2 here, minus 2 and a minus 2 iota here. Zero, zero. So this becomes, again, I multiply by, let's directly multiply by, if I multiply by half, I'll have a minus iota. And if I multiply the minus iota by an iota, I'll get a 1. So let's multiply the first row by an iota by 2 and the second row by half. So 2 will cancel 2 and iota into iota will give me minus 1, which will make it 1. And over here I'll get an iota. Here I get a minus 1 and minus iota. Now I just add the first row to the second. So again, x2 is free. I don't have to say R belongs to C. And x1 is minus iota x2. So x1 is minus iota alpha. Therefore, the eigenvector is of this form. The previous one was, the other one was of iota 1. And this one is minus iota 1. And they are linearly independent. You cannot get from here to there by multiplying with any number. So for example, if I multiply this guy by an iota, I'll get, multiplying with iota, I'll get iota into iota minus 1, 1 iota. So I don't get this. And when I had multiplied this guy with iota, I had got minus 1 iota. So there's a difference. And actually you cannot find any number which will take one to the other. They are linearly independent. You can check their linear independence in the complex plane. Let's call it x1 and call it x2. Take two complex numbers, c1 x1 plus c2 x2, so that you get a 0. So I get minus iota c1 plus iota c2 plus c2. So it's telling me that c1 has to be equal to minus c2 for this equation to hold. So then the first equation tells me that minus iota c1 minus iota c1 is 0. But that is only possible if c1 is 0. But this equation then tells me c2 is 0. So this equation holds only if c1, c2 are 0, even if I'm allowing complex values. So these x1 and x2 are linearly independent. And these are the two eigenvectors generating a one-dimensional eigenspace in for these two eigenvalues. The only difference this time was that I had complex eigenvalues. And similarly, because I had complex eigenvalues, so I was allowing my eigenvectors to be multiplied with complex numbers. And I was considering complex vector spaces. What's a complex vector space? Just consider vector space. Just consider vectors. You have these vectors belonging to your space. Then you suppose that you can multiply them with complex numbers. And if you make a linear combination and it's still inside your space, where the only difference is this time these constants, they belong to complex numbers, then it will be a complex vector space. You're just changing the numbers with which you multiply. Now, one thing you might have noticed that the eigenvalues, what were the eigenvalues? 1 minus 1 plus 2 iota and 1 minus 2 iota. 1 plus 2 iota and 1 minus 2 iota, and corresponding generators of eigenspaces were minus iota 1 and iota 1. So you can see what's happening over here. This guy is complex conjugate of the other, and this guy is complex conjugate of the other. So you have two complex values, eigenvalues, but each one of them is a complex conjugate of the other. Similarly, you have two eigenvectors, complex eigenvectors, but each one of them is complex conjugate of the other. This happens in general. Why does this happen? Well, so if your matrix is real, then what will happen? Matrix is real, but eigenvalues are not. Then this will happen because you have this where A has real entries. What would that mean? That if I define the complex conjugate of A by A bar, this would be same as A. Because what's the complex conjugate of A? It's that matrix whose ith jth value is just the complex conjugates of the ith jth value of I of the original matrix. So you are taking the complex conjugate of the individual value, but if A has all the real values, the complex conjugate will be A itself. Now, if I have this some eigenvalue lambda and with some eigenvector x for this A, if I take the complex conjugate of this thing, what will happen? Complex conjugate bakes on matrices and on numbers. So you are taking the complex conjugate of individual of them. But complex conjugate of A is A itself. So what is this equation saying? This says x conjugate. You had originally some eigenvector x, but if you take its conjugate, that's also an eigenvector. This is an eigenvalue equation. Eigenvalue equation. If this is satisfied, so is this. And what is this equation? What does this equation say? It says that x conjugate is also an eigenvector, is an eigenvector with eigenvalue lambda bar. So you have proved if lambda is an eigenvalue, so is lambda bar. So if you get an complex eigenvalue for a real matrix, you will definitely get its complex conjugate also as an eigenvalue. You don't even have to find the other one. You will just write it down that it will be there. And you will also know what is the corresponding eigenvector. What is the corresponding eigenspace? It's just that you take the basis vector of this eigenspace and take its complex conjugate. So this part that if you have two matrices like this, you can think of this as a matrix and this as a column matrix. Then if you take the complex conjugate, it begs. This you can prove very easily, because if you have two matrices A, B, doesn't even have to be, B doesn't even have to be a column matrix, it could be any matrix. AB, if I take the complex conjugate, its ith, jth element is equal to AIK, BK, J is complex conjugate, but these are just numbers. So on numbers, complex conjugation breaks. What is this? This is just the ith. This is just the ith. By definition, this is the ith, jth element of A complex conjugate times B complex conjugate. So it does break. Now, let's consider this very interesting property of the eigenvalues of matrices. This is an extremely important theorem. We will hopefully use it next time about similar matrices. Suppose A and B are similar matrices. What does that mean? that is A is equal to, or you can write it in any way. If A is similar to B, B is similar to A. For some invertible matrix S. I'm assuming over here A and B are both n by n, and so is S. So for in all this chapter, when you're considering the eigenvalues, they are all n by n. If this is so, then eigenvalues, if A and B are similar, then eigenvalues of B are same as those of A. So since you can find a huge number of, well, infinite number of S invertible matrices and keep making conjugation, this is called conjugation, with A to generate new B's, you have a huge set of matrices who all have same eigenvalues. If you're given one, you can generate other B's which have same eigenvalues. So in other words, starting from A, you can go to B by taking any invertible matrix and conjugating. This is called conjugating with S to get a new B. But as long as A and B are related like this, the eigenvalues will not change. It's a remarkable fact. How do you prove it? So how do you find the eigenvalues of B? Eigenvalues of B are the roots of the polynomial which you construct using the B matrix, which is determinant of B minus lambda I, and you have to put it equal to 0. In other words, just the root I have written is the root of this polynomial. But B is S, how did I have S A S inverse. Now, if I have this I can write it as S I S inverse, because S times I is going to be S, it doesn't matter. And then this S hits S inverse to give me I back. So that means I can write I as SI S inverse. Why is that useful? I can take this S and S inverse outside this whole A minus lambda I. So because of this, I can write it, this I as S I S inverse, and that can be written as lambda I S inverse. Now we use the properties of the determinant. So we know that the determinant breaks over matrices. So this is equal to determinant of S, determinant of A minus lambda I times determinant of S inverse. Now we know, or if we don't know, we can just prove now that if you have any matrices let's say x and its inverse is, it gives me the identity. Now if I take the determinant of both sides, I get this. Over here, I know that the determinant breaks down. Determinant of product is the product of the determinants. But determinant of identity is just one. So that means determinant of x times determinant of its inverse is 1. Or determinant of x is inverse as a number, it's just a number, is the reciprocal of the determinant of the inverse. A matrix and its inverse, they both are determinants which are inverses of each other. So that means this guy and this guy, they multiply to give me 1. So this means that this polynomial which I was constructing, which was the determinant of p minus lambda I got it to this point. This becomes determinant of s 1 over determinant of s times determinant of a minus lambda I. So it's a minus lambda I, which is the characteristic polynomial for the matrix A. So B and A have same characteristic polynomial. They're gonna give me the same roots. So when I put them equal to 0, implies B and A have same eigenvalues. We have proved it, and we can look at an example. So suppose, example, suppose you're given that this matrix T 1 2 2 1. What are the eigenvalues? I'm just doing it directly now. So it's determinant of, well, let me write. So that means 1 minus lambda square minus 4 is 0. 1 minus lambda square is 4. I take a square root and use a plus and minus to give me the two roots. So this gives me lambda is equal to 1 minus 2, which is minus 1, and lambda is equal to 1 plus 2, which is 3. So the two eigenvalues are minus 1 and 3. And I just pick up some matrix one, 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 2. Its determinant is 2 minus 1, 1, so non-singular. So I will be able to make its inverse. Let's quickly find its inverse. So this is what you do to find S inverse. So from here, I just add the first row, -1 times the first row to the second. I get -1 plus 2, 1. -1 comes over here. And now I add -1 times the second row above. So I get a 2 here, -1 into -1, +1 and +1, 2, and -1 added above. So this implies S inverse is 2 -1 -1 1. And then I can do the following. Construct this matrix ST S inverse. So S was 1 1 1 2. T was 1 2 2 1. And S inverse is 2 -1 -1 1. So this gives me 2 -2 0. 1 into -1 plus 2 gives me 1. Then 4 minus 1. Well, what is it? 4 minus 1 gives me 3. Then -2 plus 1 gives me -1. 3 minus 2 plus 1 minus 1. And now I get 0 plus 3 and 1 minus 1 0 0 6 1 minus 2 minus 1. So this is the second matrix I have got, and I'm hoping that it has the same eigenvalues, and if we haven't done anything wrong, it should. So I compute this to find the eigenvalues of this. Of this matrix. So I have a 0 here, so the eigenvalues are trivial to find. So it just gives me 2 roots, lambda is equal to 3 and lambda is equal to we had a -1 before. Yeah. Lambda is equal to -1. So this is a different matrix from this, but they have same eigenvalues. And the reason is they are connected to a similarity transformation. So let's stop here.